In our second problem, we look at a survey of 1,547 customers that involved several questions that required yes or no answers. The surveys were actually administered by 6 different interviewers. The results below relate to the question, I think that luxury cars are not worth the money. The whole focus of this is to see if there is a difference, a systematic difference, in the responses given according to the interviewer. So we are first asked, how much evidence is there that interviewer number 3 is different from the other 5 if we treat the other 5 collectively? Okay, so the first thing we have to do is come over here and do some calculations to fill in our table. So, for the first interview, 38 agreed, 127 disagreed, so the total number of people that interviewer 1 talked to would be equal to this one plus the next one. So a total of 165 people. I can copy that formula across and see how many each one of the interviews actually interacted with. Now we can calculate the proportion that agree. So we would say equals agree divided by out of. And we get 23.03%. I can copy that across. And I have the numbers for all of them. Now, the next thing we would do would be to calculate the standard error. The standard error is shown over here on the right with this. Now, this is the formal equation. It has p hat times 1 minus p hat all over n minus 1 under the radical. Okay, some people would skip the n minus 1 and just use n. There's very little difference in the calculations, but just so that we get the same numbers here, let's calculate equals SQRT square root. Now you can start out, this is just one of the ways to handle all of the brackets and how many you should have on the left and on the right. So if you put the square root and like that, and now we can fill in what's in the middle. So now I'm filling in what's underneath the square root sign. So the first part is p hat, which is right here, B21, p hat times, open parenthesis, 1 minus b hat, close parenthesis, oops, and okay, the square root of p hat times 1 minus p hat, divided by, let's put another set of parentheses in there just to be sure that all of this is the numerator, divided by n, which is the out of box, 165. Oops, forgot the final parenthesis. Oh well, Excel put it in for me. There it is. So square root of p hat times 1 minus p hat over n. All right, so I can copy that one across. And now we can calculate upper and lower confidence interval bounds associated with, say, plus or minus 2 standard errors. So this is easily done by saying the lower bound would be equal to the mean proportion, which is that, minus 2 times the standard error. And I get 16.47. And the upper bound would be equal to the proportion plus 2 times the standard error. And I get 29.59. Now I can copy them both over to the right simultaneously, like that. and I have my entire table filled out here. All right, so let's take a look at it and see what it means. It certainly looks like interviewer number 3 received a smaller number of agreements. He got 14 out of 116, which was 12%. The other ones are 23, 21, 24, 25, 22. So he's half of that. But this 12.07% is about 3 standard errors. If you look down here at the standard error, 3 standard errors smaller than the next smallest proportion, which was this one right here for interviewer number 2. So if the standard error is 3% and the difference here is about 9, yeah, that's 3 standard errors smaller. So yeah, that's unexpected. Now we could also try and graph this. Now the graph that is shown in your book is a little challenging to duplicate, but I'm going to try to do it easily with a scatter plot chart here. Just pull that one in. And that didn't work. So I'm going to try it again and say, let's just do the proportions. So if I click the proportion and the 6 numbers that I want and say insert a scatter chart, I'll get that right there. Now with the chart selected like that, watch this. I can just drag these corner things down 2 more and I'll get all 3 values without having to mess with the axes or anything like that. So I can see that let's add the chart element, let's add the axis titles for the primary horizontal, and this will be the interviewer. And so we can see that interviewer number 1, I also want the, let's see, add chart element, add axes, primary horizontal, axis titles, data labels. There we go, on the bottom. So the blue dots are going to be the proportion. The orange dots are going to be the lower, 2 standard errors lower than the proportion, and the green dots are the upper values. But as you can see in this interviewer number 3, wow, they are considerably lower. So you would think that perhaps interviewer number 3 is asking slightly different questions, such that he or she is influencing the answers that he's getting back. So it looks like even though they're probably talking to the same kinds of people, in other words, the population is homogeneous, it would seem like the nature of his interviewing is influencing the kind of responses he's getting. Another way you could do this would be you could combine all of the other interviewers into a single figure. And if you did that, let's see, you would have 333 out of 1,431. That's combining interviewer number 1, 2, 4, 5, and 6. So you come up with 23.3% with a standard error of 1.12. So this would be huge by comparison. So there's a better way to do this if we were deeply diving into statistics. It's called a chi-squared test, but we're not going to cover it in this class. So this is just an easy way to look at it and solve it graphically.